So we are talking about the I/O interfaces, and in that we said that, we already can you see slides? Can you see slides?
Yes.
Okay. So we said that we already discussed serial and parallel interfaces, and then we concluded that we have to design a different interface for every combination of I/O devices and computer, and that's really a complicated thing to do. And further, we want, the devices to be connected directly to this bus. So because of this, so that they can get a better speed. But because of electrical reasons, that is not possible to be done. So then the idea comes is PCI bus. This much we have already discussed. So PCI bus is actually a kind of expansion bus that extends the processor bus in a way that now you can connect different devices, many number of devices with that. And this number of devices, generally they feel like they are directly connected to the processor. But because of this, there will be a small delay. And as we have already seen in the last class, that there will be a bridge in place. Probably you can see this bridge here. So there will be a processor, and there will be a main memory, and then there will be a bridge in between, and then followed by bridge there will be a PCI bus, and then there will be different kind of devices or controllers available. So it may be a CSI controller, it may be USB controller, it may be a Ethernet controller, it may be a ISA controller, and all that. So this is basically an expansion bus. That's the point that I want actually to make here. It is actually a low-cost bus that is processor independent. So the problem that we started with is actually not there. And the biggest advantage with this kind of PCI bus is what? It is plug and play kind. It has a plug and play behavior. Can somebody tell me what does we mean by plug and play behavior? Can anybody tell me what is a plug and play? Yes.
Plug in what? Can you repeat?
Plug and play. Have you heard the word plug and play? You must have heard the word plug and play because all of you use computers. So can somebody tell me what is plug and play? Yeah, literally this means this only. And actually also this means this only. But what this actually means is, I'll talk a little later, we can directly fit in a device, we can directly power on a device after making a connector to this. And then there is nothing to be done from the user side. Software will take care of everything and you can readily use the device. So PCI bus is actually plug and play is of the nature of plug and play. Second more important thing is PCI bus is not actually designed for single byte transfer. It is basically designed for burst transfer. So there will be a large data that will be either read or written somewhere, and PCI bus is designed for this. Even if there is a single byte to be transferred, that will be considered a 1 byte burst. And there are three kind of address spaces that we talk about here. So that is memory, I/O, and configuration. Memory and I/O you are generally aware of. So memory is actually memory mapped I/O. I/O is I/O mapped I/O. Configuration is something different. We'll talk about this in maybe another 5 minutes or so. Right? So there are a few things that I have said that we are going to use it for burst transfer, that is successive memory location data transfer. It is plug and play, and it has got it supports three kind of address spaces: memory, I/O, and configuration. I/O address spaces is actually to be used with processor. So generally, when PCI bus is there is always a separate I/O space. So, I mean, it's designer's choice whether they want to use memory mapped I/O or I/O mapped I/O. And I mean, while connected to PCI bus, the devices are like they are directly connected to bus. So that's why we call it expansion bus. Right? Is it okay? Is it okay? Hello? Is it okay? Are you guys there?
Yes, sir. Yes, sir.
Okay. I start thinking like I got disconnected. Okay. So, I mean, there are two ways to actually connect it through memory. One way you have already seen, actually. Another way is you can use a memory. I mean, you can use bridge to connect the memory. So, I mean, so it's like.
So your screen is not shared anymore.
Oh, sorry. Now, is it okay?
Yes, sir.
So this is a host, and then there is a bridge. And earlier we see that there was a main memory connected here. Now the main memory can also be connected here. So this is another way of configuration. And of course, then it will be a PCI bus. And then there will be multiple SCSI, USB, and whatnot. So all of these things will be connected to this place, right?
Yes, sir.
So there are these two ways to be connected. The terminology that is used here is slightly different. Of course, many protocols use that. So the terminology used is initiator, and target. So master is called initiator, and slave is called target. And there are certain instructions that there are certain commands actually that we use. So let me show you those.
sir, your screen is gone.
Yeah, I unshared that. I'm sharing slide now. There's a problem with these kind of classes. You have to, yeah. So these are the signals that are available on a PCI bus. So first is actually you can very easily see is clock. Another is frame sent by initiator to indicate the duration of a transaction. And then there will be address lines, so 32 address lines, maybe 64 as well. And then command / byte enable. So either it will be a 4-bit command or 8-bit byte enable. And then this is more important, initiator ready and target ready signals. So it's more like a handshake. And this is actually something that makes it plug and play. I'll talk about this, how this happens. So dev cell and IDE cell is actually that makes it what you call plug and play, right? So now let's move on to this thing. A particular, you can say, transaction. So it's called a transaction. So it's a particular read operation. So you can see that there is clock, 7 clocks are there. And then there is a frame signal that is actually mentioning the duration of frame. And then for some initial time, address is being flown here. And then once the, and this is the command, and once the byte enable actually comes, now you can see that your bytes are coming. And of course, initiator ready signal and target ready signals are a must. If they are not there, no transaction can happen. And of course, which device that is being selected, that has to come. So I'll talk about dev cell in some time. So this way, actually, the transaction happens. Does it make sense?
So could you go over it just once more?
Okay. So, okay, let's see a previous slide first so that you are more aware of signals. So these are the signals that are actually is being used by PCI bus. Clock is simple, you know that. Frame is the frame length that is sent by initiator to indicate the duration of the transaction. So while this signal you send this duration of the transaction, this is actually transferring over your bus, and then address and data lines, so whether it is an address line or data line or whatsoever it is. And then command and byte enable lines. And then these handshake signals, ID, I ready and T ready, that is initiator ready and target ready signals. And then dev cell I'll talk about little later. And ID cell initialization device. So now you can see this. Just look at this. So what is happening in clock cycle 1? Processor asserts a frame to indicate the beginning of frame or beginning of transaction. At the same time, it sends the address on the AD lines and a command on the CBE line, right? So here it is indicating this command is whether, because it's a read operation, So this command will indicate that it is a read operation. Is it okay? So this all is happening in cycle 1. In this cycle, this all is happening. Now, cycle 2 is actually, using cycle 2 is only doing one thing. Now, address line will be converted to data line. You know that these are actually same. So now onwards, whatsoever there will be in form of data. And then from cycle 3, you can see that data is coming over this. And now this CBE line is actually giving byte readable thing. So earlier there was a command, and now this guy is enabling that now you can use the data for this. So all CBE lines are asserted for this. And you can see this frame signal is still asserted. So it will actually tell you the duration of the burst. So it is going to be total 4. And another thing you can see that you have a target ready and a initiator ready for the time for which this is actually transferring the data. Does it make sense?
Yes, sir.
Okay. Now let's see a different example, and stop sharing and I'll start sharing. Okay. So first thing is actually clock. So let's draw the clock. Let's number it. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, and this is, let's call it 9, right? And of course, let's draw a line here so that then the first signal will come. Which signal will be first to come? So it will be frame. So frame will be asserted first, and this will go to this point. The drawing is not very good, so just accommodate with it. What will be coming here? Can somebody tell me?
So read.
Address. It is AD, not RD. Address.
Oh, sorry.
And then after some time,
Byte enable.
data will start here. Now there is some trick here. That's why I'm discussing about it. There is some difference here. So this is byte 1, this is byte 2, this is byte 3, and this is byte 4. And then, of course, CB. So initially there will be a command. there will be a byte ready. So nothing so great about it. And then there will be, what will be there? IRDY and TRDY. So if you remember your previous diagram, and you can compare probably here it. So and maybe and of course dev cell. So So can you point out the difference between this diagram and last diagram? Can you point out the difference? Can somebody point out the difference, please? Is there a difference? Is there a difference?
Sir, isn't there a difference with target ready signal?
Pardon?
Sir, is there a difference with the target ready signal?
Yeah, in target ready and initiator ready, both there is a difference.
Sir, they're out of sync in this one.
So these are the differences. So you're asserting initiator ready. Initiator is ready for a couple of data cycles to take, and then it is getting actually it's bar signal, so it is active low signal, so it's getting high for some time, and then again it is getting asserted. Similarly, target ready is actually getting unready for some time, and it is again getting ready. So initiator is actually getting some problem, and as a result target is also getting some problem. So you can see that this third data byte is taking a long time, and it is only being transferred in this duration. So in this whole duration there is no transfer happening, and that's why this third byte is getting elongated. Getting my point? So the read operation starts the same way, and first two words are transferred. And when target sends the third word, at that time initiator is not able to receive that. So that's the problem, right? So it does not receive, and the target maintains the third word for longer duration. Are you getting my point? Are you guys able to understand this? It's a read operation. So target is sending something to the master or initiator. At some point of time, master is interrupted or something like that has happened, so it is not ready. And because it is not ready, so the data has to be held up for some more time. And after some time, target is also not ready. So that's why it is going for a longer duration. Is it okay? Is it okay? Hello?
Yes, sir.
Fine. So the point is only this, that this kind of thing may happen, and because of this, the transfer will only delay, it will not be suffered. Another thing is, you can see that address is there only for this much duration. So actually what happens, that address is only required till the slave, or you can say the, in particular in this case, target is selected. So till that time address is kept and then it is freed. So this saves a lot of cost. So these are the few things that I want to discuss about this timing diagram. Is it okay? Shall I go ahead? Shall I go ahead? Okay, thank you. I'll just delete this. So now we said that it is a plug and play thing, right? So in plug and play thing, while you are connecting a device, you don't have an address for the device because so far no address has been assigned to that. So how to handle that situation? So that is something that for that this configuration address space is used. We'll just talk about that configuration address space. So when an IO device is connected, I hope you are able to see the slide now.
Yes, sir.
Okay. So when IO device is connected to a computer, so first of all, we have to understand that what is the address that this device has. So, there are several things that has to be done. And the most important is identifying address. So, there will be some physical things like connecting jumpers and all. So that we are not actually talking about here in this case. Once your device got the address, then you can do the communication through the software and all that. So once you push the device in the slot, make some jumper connection and all that, electrically it is powered on. So the biggest challenge is getting an address. So how to get an address, that is being taken care of by this device configuration space. So in this, every device interfaces with a small configuration memory that is of ROM type, and that stores the information about the device. So, this configuration is always accessible in configuration address space. So then PCI software reads this memory whenever the system is powered up or reset, and determines what kind of device it is. So it may be a printer, it may be a keyboard, it may be an Ethernet interface, or anything of this kind. And then addresses has to be assigned. So generally, what happens, you push address into the address buses, but here it is slightly different. So it happens through signals. So the motherboard in which device connectors are plugged has IDSEL pins. So that is selection ID pins, and this is connected to one of the upper 21 address lines, so AD11 to AD31. Hence, when a device is selected for a configuration operation by issuing a configuration command, an address depending on which ID select pin has been connected. So 1 to 21, actually 0 to 20 has been assigned to this. Whereas the lower address lines are used to specify the operation and content of the device configuration ROM. So once this happens, now out of these 21 locations, host can identify the device, and then device may request address in IO space or in memory space, whatsoever kind of configuration it is. And in result to that, the address is assigned, and not only address, along with that priority is also assigned. So because it's a device, so it has to be assigned a priority. And on the basis of priority, which interrupt pin it has to use. So there are many interrupt pins that will be there. So depending on priority, which interrupt it can, what kind of interrupt it can make. So a priority will be assigned, and an interrupt pin will be assigned to that. So this whole process happens after plugging the device. And so once you plug the device, the configuration memory will be read. And depending on which pin in motherboard it is, the address will be there. And device will request for a regular address. And a regular address in memory space or IO space will be taken. And priority will be assigned. So this all happens. So this is basically plug and play idea. Do you understand this? And you can probably see that there is no intervention of user required in this whole process. So once you plug it, you don't need to worry about anything. Does it make sense to you? And of course, you can also understand that you can use only 21 devices to connect, because there are lower address lines that will be used for transferring the data in configuration memory, and what kind of operation this will also be specified using that. So out of 32, 11 will be used for that configuration data transfer, and these 21 will be used for identifying the device. Does it make sense? Hello? Does it make sense? Am I there? I got disconnected. Yeah, does it make sense? आप लोग हैं या चले गए? Priyanshu is saying yes, sir. Okay. Any other guy who could not appreciate this or who could not understand this? And by the way, number of students got decreased from 45 to 33. क्या हो गया? So it's a playing time, it looks like. Hello. Is it okay? Except Priyanshu, others can at least speak. Priyanshu is saying his health is too bad to speak. Others can at least speak up. Is it okay? Is it okay? I don't know why you guys take so long in speaking up. Is there a problem? What? Tell me. Student number is decreasing every time. So it is now 32. Manasa, are you there? Sleeping?
Sir, I've got sore throat actually. Sore throat.
Sore throat.
Yeah.
Okay, anyway. So, assuming that you understood this, although the way you are responding to doesn't look like that, but still assuming that you understood this device configuration idea, I'll go ahead. So, this is all that I want to discuss about PCI bus. Next, I'll discuss about SCSI bus. So, as most of you must be aware that SCSI stands for Small Computer System Interface. So, this is actually used for data transfer between disks and hosts, and you can have a data transfer with a distance. So earlier the initial versions of SCSI were actually transferring the data with a speed of 5 Mbps, and you can transfer the data up to 25 meters of length. 50 pins were there initially. So 50 pins, 5 Mbps and 25 meters. That was the start that it took. And now there are various options. You can have as much as 80 pins. And data transfer rate also got significantly increased. So from 5 Mbps to now it has become as high as 640 Mbps. And of course, that will certainly depend on the length of the cable and how many devices you are connecting with. If you are putting a longer cable, maybe you have to compromise with speed. So that's the point that has to be taken care of while talking about this. Another thing that is important to discuss about this is there are two types like the previous PCI bus. One is initiator and another is target. It is same as the previous thing. So, both the sides will be having controllers. So, there will be a processor there will be a processor side controller, and there will be a kind of target side controller. Now, the point is, if you have used hard disk, I don't know, now systems there is no hard disk or hard disk with less capacity. But if you have used hard disks, you must be aware of that these are actually disks with a system where disks rotate. And in disks, there are sectors where you store the data. And it's not, generally stored data is not contiguous, because in sectors there is some space where you have to write some firmware, or you can say already written programs. Then few sectors may be unusable because of your disk problem or any other kind of problem. So the point is you are transferring bulk of data, and that bulk of data will not be available on a single sector, neither it will be available on contiguous sectors. So that means you have to travel sectors to sectors for transferring this kind of data. And this rotating disk and transversing sectors to sectors will take delay as high as of the order of milliseconds. And here we are talking about the speeds like 640 Mbps or at least 5 Mbps or so. So, I mean, that is definitely not going to work with this kind of delayed or, millisecond delay kind of system. So, how to handle that? So, to handle that, there is a way by which it performs. So, initiator has the ability to select a particular target and to send commands specifying the operations to be performed. The disk controller operates as target and it carries out commands it receives from initiators. And then the initiator establishes a logical connection with the intended target. So once a connection has been established, the connection need not be consistent all the time. It can be suspended and restored as and when required. So, connection will be there, but it will remain suspended. So the idea is once the target had specified that, okay, this sector has to be used for transfer the data, data transfer will happen, and then the connection will be suspended. And then SCSI will be using some other, will be doing some other job. And by the time this disk rotation and all will happen, and then again data transfer will happen. So this suspension and restoration actually, helps in performing this data transfer operation and achieving good amount of speed by that. So for example, if a read operation has to happen where a SCSI controller is acting as initiator, when initiator actually starts the data transfer, it selects target controller and hands over control to bus to it, and then target starts an output operation, and in response to this, initiator sends a command specifying the required read operation, and then after that this required read operation, there will be a disk seek operation required. So because a disk seek operation is required, so target will send a message to initiator that now this connection has to be suspended, and then after some time target will again send a command to disk drive. Target will again send a command to initiator that now the required thing has done, and this connection will be restored. So this is the way it happens. Any confusion about this? Is it okay?
Yes, sir.
Okay. So let's move a little ahead. So these are the signals that is actually used over SCSI bus. So first you can say that there are different categories. The first category is data. Another category is phase. Another category is information type. Another category is handshake. And another category is direction of transfer. And then other signals. So let's start with data. And you can see that there is a dash before all the signals. So dash represents that these signals are actually active low signals. So it will be asserted when there is a low thing. So first category is data. So you can see that DB0 to DB7. So data lines carry 1 byte of information. And then one is parity bit. So the parity information will be carried away. Another is BS phase kind of category. There you can see that BSY and SEL is used. So BSY is used for, these are actually used to resolve the conflict. We'll talk about that maybe after this. So when there are more than one takers of a SCSI bus, how to resolve the conflict. So this is used for arbitration. And then CD, so whether it is a control signal or it's a data signal, control bit or data bit. And then MSG's masses indicates that information, what kind of information is being transferred into a message. And then handshake, so there will be a request and there will be an acknowledgement. And then another thing is the direction of transfer, so whether it is an input signal or it's an output signal. And then there are other signals like ATN and RST, you can see that. So ATN is asserted by an initiator when it wishes to send a message to target. And RST is the reset, causes all devices controls to disconnect from the bus. And assumes that now it is a startup thing. So these are the bus signals that SCSI bus actually carry. Any confusion about this? So now let's talk about main phases involved in SCSI transfer. So one is arbitration. We'll talk about arbitration after some time, but the only idea is if there are more than one controller requests for the bus, how to resolve that. So first of all, whenever a transfer has to happen, if required, arbitration phase will take place. And then selection. So in arbitration, somebody will win the arbitration and then he'll perform the required selection by selecting the target by STL line. And then, of course, once the selection has been done, a BSY line will be asserted by the target. And after arbitration and selection, the information transfer will take place. So in information transfer, handshaking signals will be there between initiator and target. And at the end, the target will release the BSY signal. And after this, the logical connection will be suspended and target is ready to restore it. So, again, reselection will happen after some time. So, target must first gain the control of the bus. And then again, arbitration will happen, and after winning arbitration, and all that process will happen. And then again, the selection will happen. Is it okay? Is it okay? So now let's look at the arbitration thing. So in SCSI bus, there are priorities assigned to different devices. And of course, high priority will win over low priority. 7 will be the highest priority. And 1 will be the lowest priority. So this way this connection happens. So whenever a busy signal is asserted, devices see that what are the other devices that are connected. So for example, here this DB2 and DB6 are contending. So this is the arbitration phase. This phase is the arbitration phase. So as soon as they realize that there was a busy signal, and some of them would have put in a busy signal. So in this case, DB2 and DB6 has asserted a busy signal. So they'll say that which has actually trying to make the transfer. DB2 will realize that okay, DB6 is trying to make a transfer, so it will withdraw and it will go back. Whereas DB6 will keep on. DB6 will select DB5 because it wants to make a transfer to DB5. So a DB5 will actually assert a busy signal now. And on the basis of this busy signal, now transfer will happen. So first of all, a busy signal will be asserted by the devices, those who want to use the bus. They will see if they are the devices with the highest number. In fact, we should say controller. So they are the devices with the highest number, or if there is any other device that has a higher number. If they are the devices with the highest number, they'll keep on making the transfer. If they are not the devices with the highest number, they will withdraw. And then the one who is with the highest number will actually get the information that he has won the arbitration. And after that, he'll choose a target. Target will now assert a busy signal, and the data transfer will happen followed by that. So we have already seen previously that there are phases like arbitration, selection, information transfer, and all that. So this arbitration and selection is being shown in this diagram. Is it okay? Does it make sense? Does it make sense?
Yes, sir.
Any confusion about SCSI or PCI?
No, sir.
So now we'll move on to the most famous bus. What is the name of that most famous bus?
USB?
USB, exactly. So why USB is so famous? Can somebody tell me? Can somebody tell me why USB is so famous? All of you use USB, right? Is there anybody who does not use USB? Any idea? So first thing with USB is it was actually evolved with a group of industry players. So everybody agreed on this standard, and that makes it most useful. So now because everybody's agreed, so everybody's coming up with the USB thing. Another important thing is it is a serial bus. So you don't have to compromise with the length, and you can go for a longer length for all kinds of devices. So there is no skew effect and all that is going to come. Third thing, it is plug and play. So you don't have to do any configuration with that. PCI is also, of course, plug and play. So USB is. So you just have to play, You just have to plug the device into the port, and rest everything will be taken care of. How that will happen, we'll talk about that. And then there are number of devices that you can connect. So you can connect as many as, maybe 256 devices or so. And it is very easy to do. So you can anywhere make a hub and connect more devices. So the hardware architecture, right, is pretty simple to use. Right? Is it okay?
Yes, sir.
And it supports the variety of operations. So it also supports a keyboard that has a very small amount of data to transfer, maybe 100 bytes per second. And it also supports high-speed data operations like 480 Mbps or so. It also supports the asynchronous data transfer where the time of reaching is not important. It also supports the kind of data that is isosynchronous, for example, voice data. You cannot afford a delay into that. So these all kind of supports it provides, so that makes it so useful and what you call ubiquitous in a way. Right? Is it okay?
Yes, sir.
So this is the kind of tree structure that USB uses. So there is a host computer, there is a root hub, and then there are multiple hubs. So you can have hubs, in multiple layers, and then you can connect devices. It is also possible, probably you can see that with this hub, you are connecting IO devices and you are connecting hub. And then this hub is able to accommodate more devices. So what happens actually, these all, whether it is a hub or it is an IO device, all are assigned an address of 7 bits. So in a way, from root hub, every hub or device is actually typically behaving in the same way. And whatsoever comes from root hub is actually being transferred to all the hubs and all the devices. And it will be useful for someone. So only that device will respond, no other is permitted to respond. So there is a kind of polling when it is coming from root hub. And whosoever is being polled, that IO device will only speak up or will make some data transfer. So in a way, there is no conflict as such. Right? Is it okay?
Yes, sir.
So that makes it, very easy to handle. And then there may be a condition that there is a host computer. And then there is a root. And then there is a high-speed link. And then there is a hub. And then there is another hub. again connected with high speed. And then there may be devices connected with it. So one is at high speed and another is at low speed. So in that case, I mean, some devices, let's say, operating at low speed. So whole system will not actually move on to low speed, rather data transfer this till this point will happen in full speed, and at this point it will be happening low speed. So in that way, this link will not actually understand what is happening there. So I mean, full speed capacity can be used even if you are using some low speed devices. And so these are like, I mean, pipes where data has to transfer. So, I mean, this way it happens. Now, one important thing comes is addressing, because it's a plug and play thing. So, how addressing has to be managed? So, how addressing has to be managed, that is one important thing. So, what happens? So, for example, this is your hub, and this is your another hub, and then this is there is another hub, and then there are devices. And here you have few devices. And then you have another hub and things like this. So whenever a USB is connected to a host computer, where it appears as a single device, the host computer communicates with individual device attached to USB by sending packets of information, and that is forwarded to the appropriate device in USB tree. So each device on USB is a hub or device, as I have told you, is assigned a 7-bit address. Importantly, this 7-bit address is local to this USB tree. So this 7-bit address is only known to this USB tree. Nobody else means the processor will not be aware of this. So the processor bus is going the way it will go, and here there will be a 7-bit address that will be actually taking place. So how these address assignments have happened, what address has been assigned, and all that, there is no relation to this. So this is entirely this device job, and it is its information only. It does not have to be shared. And the whole root hub keeps on polling to all the hubs and keep on collecting information for new devices and for disconnected devices. When host is informed that a new device has been connected, so it sends a sequence of commands to the hub and then to the device, to understand its capabilities and send configuration information to the device. So whenever a device will be coupled, and this polling process will tell host that this device has been connected. So it will understand the capability of the device, and then as per that, it will send a configuration message to the device. So probably you would have seen that, whenever you connect a USB device, you see that something of this kind, that acquiring address or configuration is happening. I don't know now, because systems are so fast, maybe you are not able to see that. But if you will try to see it properly, probably you will still be able to see that. So once this whole job is complete, device is now addressed device, and it will begin normal operation, and now there is nothing else to be done. Similarly, when a device will be removed, then this similar procedure will be followed, and this address will be actually cleared in this. So the locations in the device from which this data transfer takes place, these are called endpoints. So where you send your status control and data registers, and these endpoints are actually having 4-bit of address. So if there is a 4-bit of address, you can easily understand that there are 16 endpoints possible. I think that should clear the board. So 4-bit of address or endpoint. So that means you can have as many as 16 endpoints, right? So this is about the feature of being plug and play. Now let's move on to the protocol. No, not only 24 students are there. Where are other students? Manasa?
Yes, sir.
Students are decreasing every time. From 44 to it's now 24. What is happening?
Sir, I do not know it. They have left. Sir, they have left. I don't know why.
Okay. Okay, let's complete USB and then we'll stop. So, this is the kind of packet structure for USB. So, there is 3 kind of things that we have to understand. One is the packet identifier feed. So, in USB packet, first 8 bits are reserved for this packet identifier. And then this packet identifier, you have actually 4 bits repeated twice. So it is not actually repeated. First 4 bits are actually complemented and put in into the location. So for example, here we have PID 0, and here we have PID 0 bar. Here we have PID 1. Here we have PID 1 bar. PID2, PID2 bar, and PID3 and PID3 bar, and like that. So that means we can have as many as 16 different kind of packets. That may be control packet, that may be acknowledgement packet, and that is again control packet, and that may be data packets as well. So this is first 8 bits that are actually being used for identifying the packet type. Then there are 2 kind of packets that have been shown in the diagram. One is token packet, that is basically a control packet, where you can see that first 8 bits are actually reserved for packet type. And then there is an address, and then there is a end packet word, and then there is a CRC16, that is checksum. So this is actually used to distinguish whether it is a in packet or out packet. So this may be actually used for any kind of control purposes. And acknowledgement packets, for example, only have PID packets. And this PID actually helps in understanding that what is the kind of packet that is actually being told by PID is right or wrong. So that is actually a little important. So it is being done like this. And then you have data packets where you have a 0 to 8192 size of data, and then a checksum. So this is basically the USB packet format. And so this is important to understand that all the packets in transfer has been assigned value 0 and value 1. So either you will be transferring data packet 0 or data packet 1. So once you will receive the acknowledgement for data packet 0, then only data packet 1 will be transferred. So this kind of data transfer happens. So so you can always receive the packets in a reliable fashion, and that too in a sequenced manner. So as long as you are not receiving acknowledgement, you are not sending it. When you will receive acknowledgement, after that a token will be sent that it's outgoing packet, and then a data will be sent. So you can see that there are 3 points: host, hub, and IO device. So first of all, transfer will be happen from host to hub, and then from hub to IO device. So this way all the data transfer happens. Make sense? Does it make sense? Is it okay?
Yes, sir.
Last thing is that we want to discuss about USB is isochronous traffic on USB. So the idea is packet should not be delayed. It either may be dropped. It should either reach on time or should be dropped. So this is generally used for voice transfer and all that. So devices that generate or receive isochronous data requires a time difference that I have already said. And the USB is divided into frames of equal length, and if it is not reaching, it will be dropped. The root hub generates a start of frame control packet precisely once over 1 millisecond to mark the beginning of one frame. And arrival of SFF packet any device constitutes a regular clock signal. So in a way, this root hub and the device is actually getting synchronized using this SFF packet. And if it is longer than that, the SFF packet carries a 11-bit frame number. And then there will be input-output transfer. So, that means now you have partition the whole duration into a slot of 1 millisecond and where any device can make a transfer. So this is the basic idea of this. And now let's see the frame structure of isochronous packets, and then we'll just see the electrical properties and we'll finish it off. So of course everything starts with 8-bit PID. So here it will be PID of course 8-bit length, and then there will be a frame number, and then there will be a CRC, and here we use CRC5. So this is actually 5-bit. So these 24 bits actually make a SOF packet, start of frame packet. So if you are talking about a 1 millisecond time frame, how will it look like? Just have a look on that. So first of all, there will be a SOF. That means start of frame 24 bits. And then there will be a token packet. So let's call it TL. And then there will be a data packet. And then there will be a token. And then there will be a data. And at the end of this frame, again, there will be a start of frame. It will keep on going like this. So this way, isochronous transfer happens. Any confusion about it? Okay, so if there is no confusion, we'll just look at the electrical properties and we'll just finish it off here. So, electrical characteristics wise, cable used for USB connection consists of 4 wires, you already know that. And 2 are used for carrying +5 volts and ground. So you already know that hub on IO device may be powered directly from the bus, so no external power is required. And other 2 wires are used to carry data. And because it's a serial communication, so you don't need to worry about more than 1 cables or skew or anything. And things like that. And then different signaling schemes can be used for this. So this completes the discussion for USB, IO interface. From the next class onwards, we'll be discussing the memory operation where pagination and cache and all will be discussed. So see you in the next class on Monday. Okay. If any question, you can ask, please.